Hey guys, I'm back. Today's lesson is on properties of rational exponents. So we're going to discuss how to simplify some of these expressions that have the rational or fractional exponents. So reviewing that first property, product of powers, we typically will add up those two exponents. So the same process is going to apply even when our exponents are fractions. So if I have two base numbers that are the same and they're being multiplied, then each of those exponents can be added together. So this will basically become 3 to the 1/2 plus 3/2, which when you add up those two fractions, you get 4/2, which of course simplifies to 2, and then that can further be solved all the way to 9. So let's try a few examples. And again, any point throughout the lesson when you want to try some examples on your own, it's highly recommended that you pause the video, try the examples on your own, and then restart it to check to see how well you did. So the next example, 5 to the 1/2 times 5 to the 1/4, we're going to add up those two fractions, the 1/2 and the 1/4. Remember, when you're adding fractions, you're always using a common denominator. So this here is really 2/4. So that gives us 5 to the 3/4 power. Now you might remember from yesterday's lesson, we can also then rewrite that in radical notation and everything, but we're just going to leave it like that for now. Okay, the next one, we have 2 6s, 6 to the 1/3 times 6 to the 1/2. So for this one, you would just be, again, adding up those two fractional exponents there. You're going to need a common denominator, which would be 6 for each of these. 3 times 2 is 6, so that becomes 2 6. 2 times 3 is 6, so this one becomes 3 6. And then, of course, when you add those up, you have 6 to the 5/6 power there. And then the third example, we're dealing with a base of x for these. So we're adding up those three fractions, 1/4, 3/8, and 5/12. Again, you would need your common denominator for these three fractions as well, which would be 24 for all these. So 3 times 3 is 9, 12 times 2, 24, 5 times 2 is 10, 4 times 6. And then when we add up those three, 6 plus 9 plus 10, we have 25. 24th as our exponent. Okay, so now the second property that we have done before, earlier in another chapter, was the power of a power property. So we had a base number raised to a power, and then that whole term was raised to another power. And typically in that situation, the two exponents will get multiplied together. So same thing applies even if the exponent is a fraction, doesn't matter, the same property, we're still going to use that. So we're going to multiply these two. So here I have 3 over 2 multiplied by 2, and of course in this case the 2's would cancel, so we would just be left with 4 to the 3rd power, which if you can solve it, you can work it all the way out to 64. So now let's try these three examples. So again, we have 3 raised to a power, and then that is raised to another power, so we're going to multiply those two powers together. So 1/4 times 2/3, that's going to give me 2 over 12, which of course simplifies to 1/6. All right, the next example here, we're going to again multiply these two powers together. So we have 3 over 2 times 1 over 5. That, of course, is 3 over 10. So remember, when you're multiplying fractions, you just multiply the numerator straight across, you multiply the denominator straight across. And finally, for number 3, you're going to multiply these two. Now remember, any whole number or integer would really be over a 1, right? So this is going to become 7/5 times 10, or 10 over 1. Which would equal 70 over 5, and that of course could be simplified to m to the 14th. And that's how we use the first two properties. So now let's take a look at the next two properties. So the next one is when we have a power of a product. So this was the property we had gone over in an earlier chapter. Basically, the power kind of has to be brought over to each number or variable or factor that's inside those parentheses. So let's say, for example, we have 9 to the 1/3 power times x to the 7th, and that whole thing is raised to the 3/4. That 3/4 power is going to have to be applied to each of these, being multiplied to both the 1/3 and also the 7. So this is going to become 9 to the, and then you're going to multiply those two fractions together, and then x, and you're going to do 7 times 3/4 to get the exponent for the x. So for the 9, when you multiply 1/3 times 3/4, you could get 3/12 and reduce it, or you could simply just cross cancel out those 3's. You would have 9 to the 1/4 power. And then when you multiply your 7 times 3 and your 1 times 4, you would have 21/4 for your exponent on the x. So now let's try a couple examples. So for this one here, again, this is just a positive 2 that's going to be kind of brought over to each of those numbers. So we have 8, and then the 1/2 times 2, and then we're going to have 5 raised to the 1/3 power times 2. So of course 1/2 times 2, those will cancel, so you just have 8 to the 1st power. And then over here, 1/3 times 2 would be 5 to the 2/3 power. And for number 2, we are going to multiply the 1/3 times the 2, and then the 1/4 times the 2. Again, bringing that exponent on the outside of the parentheses to each of the factors inside. So this will become 27 to the 2/3 power times 6 to the 2/4, which of course would reduce to 1/2. Now the next property we're going to review with these rational exponents is when we have a negative exponent. So as you might recall, whenever you have a negative exponent, we want to get rid of that negative on the exponent, so we're going to have to do that by writing it on the opposite side of the fraction. So if I currently have 25 raised to the negative 1/2 power, this is really over a 1. So in order to make my negative 1/2 become a positive 1/2, the first thing I do is move that down to the bottom like that. That way my 1/2 power can now become a positive. Now, of course, you could further work some of these out if it's something that you could solve. So 25 to the 1/2 power is the same thing as the square root of 25, which you might remember from the last lesson. So this can actually work itself all the way out to 1/5. If not, you can always check it on a calculator just by putting in exactly as you see it, 25, raise, and then if you need to, you may need to put your exponent in parentheses, 1 divided by 2 in parentheses, depending on what type of calculator that you have. All right, so then let's do a couple of those examples. So this one here, if it's over nothing, that's really over a 1, right? So we're going to move this 13 to the bottom, making that exponent a positive. Same thing on the next one here. This is really over a 1. So we're going to move that 27 down to the bottom, making that exponent a positive 1/3. And then over here, you have kind of two choices. One option is you can distribute them and then move them or flip them where you need to put them. Or if the entire set of parentheses has that negative exponent, you can move the whole thing to the bottom. So either option. I usually prefer to get rid of the parentheses first, but it's really a personal option. So if I do 4 times the negative 1/4, that gives me a negative 1. And then 4 times negative 1/4 there will give me another negative 1. And then of course both of those would have to move to the bottom. And 2 times 3 is just going to be 6. Now, option 2. If you did move the whole thing down to the bottom to begin with, like that, then that 1/4 would have become a positive 1/4. and then you would have just kind of progressed from there. So you would have distributed those, getting just 2 to the first times 3 to the first, which would have still given you that final answer of 1/6. So either option for that. And that's it. And let's move on now to the quotient properties. Okay, so with our quotient properties with rational exponents, remember when you have the same base, they're both raised to a power and you're dividing, you're going to subtract the two powers. So let's take a look at the first example. So if we have 6 to the 5/2 power divided by 6 to the 1/2 power, we're going to subtract the power of the numerator minus the power of the denominator. Now in this particular example, both of them have the same common denominator of 2, so we can just go ahead and subtract them. That gives us 4/2, which of course simplifies to just 2, and 6 squared is 36. So let's try a couple examples with that property. So here we have the same base number, they're both 12. So we're just going to subtract the exponent of the numerator minus the exponent of the denominator. Then because they are common denominators there, we're just going to subtract the 5 minus 3. We get 2/8, which of course simplifies to 1/4. Example number 2, if you remember, there's no exponent there. It's really a 1, so don't forget about that. It's not a 0. So now, because they're the same base, we're just simply doing 1 minus 1/4. Now this time we do not have common denominators because a 1 is really a denominator of a 1. So we would want to make them both the same denominator, which in this case would be 4. So it's really 4/4 minus 1/4. So 4/4 minus 1/4 would be 3/4. So our answer to that one is 6 raised to the 3/4 power. And then finally, our third example of that type, we have our two bases of n. Again, we're going to subtract the exponent on the numerator minus the exponent of the denominator. This time they do have different denominators, so we're going to want to find that common denominator, which would be 21 in this case. So 3 times 7 is 21, 2 times 7 is 14, 7 times 3, 21, 4 times 3, 12. And then when we subtract those, we end up with 2/21 for our exponent. Now the other quotient property is power of a quotient. So that's when you have that fraction or that division problem inside the parentheses. The exponent is on the outside, which means it's going to be applied to each of the numbers or variables on the inside. So if we take a look at example 1 here, we have 25, which will get a 1/2 power. We also have an 81, which will get that 1/2 power. Now, in both of these cases, I noticed that these are perfect squares. And as we learned in the previous lesson, the root is the number on the bottom, the power is the number on the top when we go from rational exponent notation to radical notation. So because these are perfect squares, and these will be square rooted if I put them in that radical notation, I can actually do that, and you don't even have to write it. If you recognize it, you could just do that in your head, right? Square root of 25 would be 5, the square root of 81 would be 9, and of course we don't need to raise anything to a first power because it would just stay the same. Now the next example, we've got two options here. For both of these actually. So now this first option, we would just continue with the property that we're working on. So we have 12, and then we multiply those, we're gonna have 2/3, right? On the bottom, we still have our base 4. 1/3 times 2 is also 2/3. So now, you might be saying, okay, well what do I do now? Well, the thing is, if both of these have the same exponent, you can kind of just go in reverse of what we just did, and you could just write it as 12/4 raised to 2/3, right? So in one sense, we are kind of distributing that exponent to the numerator and the denominator. In this case, since they have the same one, I'm just going to write it outside the parentheses because 12 divided by 4 can simplify to just that 3, and that's really where we want to go. Now, some people might have noticed that in the beginning, like if you have the same exponent here, 12 to the 1/3 divided by 4 to the 1/3, you could have condensed that from the beginning and just made it 12 over 4, which is 3 to the 1/3, and then distributed that 2 out, but either way. So same kind of concept with number 3, whether you want to do, bring this 3 over first, or you could just realize 18 divided by 9, since they have the same exponent, you can simplify it that way as well. So I have 18 to the 3/4, 9 to the 3/4, and then I notice since they're the same, I can just write that 3/4 outside the parentheses like that, making, showing that it goes to both, and then 18 divided by 9 is just 2, so I can kind of finish simplifying that all the way out. So many of the exponent properties that we talked about also apply when we're dealing with radicals as well. So just as a little reminder, we had looked at the power of a product property, and we had also looked at the power of a quotient property. And both of those properties are very similar to really what we can do with the radical expressions as well. So if you think about it, like this little exponent here would have to be applied to both of those numbers being multiplied inside. Same kind of thing happens with the radical. So whatever root is being applied here, if you split that number up inside into different factors, you can write them as each their own radical with that same root. The other property that we just finished talking about with the quotient, same kind of property applies here with the radicals. So if you have a radical with some sort of fraction inside, if you can split it up into a separate numerator and denominator, they would each get that root there. So let's take a look at a few examples. So right here, both of these are cubic roots. We have a 4 and a 16. Now, if one of these were a perfect cube, then we might just want to solve that part out, but neither of those are. So then we would want to put them back together, and because they're both cubic roots, when we multiply 4 and 16, it would still be a cubic root, so we would get the cubic root of 64. So now at this point, you might think back to a previous chapter where we had simplified radicals. So if 64 is a perfect cube, which it actually is, you could check it on your calculator, you would know that it's just going to equal 4, okay? But if you didn't know that, you would do that little factor tree like we've done in the past, right? Now I could break this up into 4 and 16. I could break it up into 2 and 32. It doesn't really matter. You just keep breaking them down until you have all prime numbers. So if I make my little factor tree here, okay, I end up with a 2, and 4 more 2's right there. Now remember, this is cubes, so when we had done this with square roots, we were looking for pairs of numbers, but now we're going to be looking for groups of 3 or triples. So I have 3 2's right here, and I have 3 2's right here. So I would take out 1 2 for each of those groups. 2 times 2 is 4. That's how you could simplify it as well if it wasn't something that maybe you knew off the top of your head or you could do on a calculator. All right, so taking a look at example 2, this time we're setting up the two radicals as a quotient. So whenever you can, if this divides evenly, it'll eliminate that fraction completely. So that's always the way to go since these are both even numbers. 162 divided by 2 can be written as 81. Notice these were both 4th roots to begin with, so my answer will also be a 4th root. Then you can kind of look at it the same way we did with number 1. Check it on your calculator. Is there a 4th root of 81? Does it work out to a nice whole number? So 4th root of 81 actually does equal 3. So we could just be done there. But if you did need to do that factor tree to figure out what factors there were and all of that, we'll get to that. But that can also be done. All right, so now taking a look at number 3, all 3 of these are 6th roots. So you can then multiply or divide because they all have the same root. So a couple options here. If you have 8 times 16, I believe that's 128. And then of course, because these are still both sixth roots there, you could do the 128 divided by the 2, which gets you to, let's see, 64. And then if you solved it out from there, this one actually will be solvable and you will get 2. All right, number 4. Now this time, the smaller number's on the top, so even though we can't divide it evenly, we could reduce that fraction because they're both cubes. So sometimes that helps you, sometimes it doesn't. There's no way to know until you check it out. But you're gonna always have to have your answer simplified anyway, so you might as well reduce it if it's possible. So 4 over 32 would reduce to 1 and 8. And notice that I kept them both in cubic roots since the originals were both in cubic roots. And this one now works out kind of nicely because the cubic root of 8 on your calculator is actually just 2. 2 times 2 times 2 is 8. And the cubic root of 1 is also just 1. So we could work it all the way out to the 1/2. All right, so a couple more. Now, getting back to that first example where I kind of was showing you how you could have broken down that 64 using a factor tree if you didn't know that it was a perfect cube. That's what we're gonna get into in these. And just like I mentioned, if you're doing something that's a perfect cube, for example, or you're simplifying something with a cubic root, you want a group of 3 of the same number in order to take that factor out of the radical. If it's a 4th root, like in number 6, you're gonna want a group of 4 of the same number to take that factor out. And for 5, and so on. So for 54, again, when you first start breaking that down to see, you know, what factors there are, you can break it up into anything that pops in your head first. So whenever it's an even number, I always think it's kind of nice to just divide it by 2 if you can't think of anything else. So I'm pretty sure that's 2 and 27. Now, 27 can't be divided by 2 because it's an odd number, but I do know that 3 goes in 9 times. And then 9, of course, can be broken into 3 and 3. So I have 2, 3, 3, and 3. So like I said, because this is a cubic root, you would need a group of 3 of the same number. And notice that we have 3 3's here. So that means we can take the 3 outside of the radical, and this extra factor, this 2, would have to stay inside of the radical, and it still maintains that cube. So it's 3 times the cubic root of 2. That's how you would simplify that one. Okay, number 6, 64, but we need a group of 4 of the same factor in order to remove it from the radical. So however you want to break up that 64, you can do 2 and 32, you can do 8 and 8, whatever you feel like doing. And then I'm going to do each of these as 2 and 4. And then we have a couple more 2's there. So again, I need a group of 4. So I have 1, 2, 3, 4 2's. So I know I get to take one of them out. That factor comes out. But I still have these extra 2's left inside. So then you're just going to multiply them back together, giving you 2 times the 4th root of 4 as your answer. And then finally, the third example here, 12, 15. And I'm pretty sure that 5 goes in there. So let's see, 5 goes in 2 times. I think it's 243. Double check that. Yes, okay. Then 243 can further be broken down into 3 and 81. And of course, 81, you got your 9 and 9, 3 and 3, 3 and 3. Now, even if you use a different strategy to get there, you should still end up with 1, 2, 3, 4, 5 3's and 1 5. Now, because we have 5 3's and it's a 5th root, I get to take out a 3, just 1 for the group of 5. And then my leftover factor, which didn't have any others like it, was the 5. That would stay inside, and that would be my answer for that. I encourage you to pause the video at this time if you'd like to try those 2 on the side, and then turn it back on when you're done and see if you got the right answer. So we take a look at number 1 here. We're going to do 72. So if I break down my 72, 2 and 36, 36, 6 and 6, 2 and 3, 3 and 2. So I have 3 2's, so my 2 was able to come out there. And then I had 2 3's left over. So those are going to stay inside, and then you have to multiply them back together. So that would be your answer for that one right there. And then finally, this last one, we have 567. So you want to break that down however you'd like. So I think I broke it down into 7 and 81. 81, of course, is 9 and 9, 3 and 3. So again, we need a group of 4. We have 4 3's, so I get to take out the 3. And then that one extra 7 stays inside, and that's your answer for that one. And that's how you're going to work with the radicals. Okay, so next we're going to be simplifying some of these radicals that are set up in quotients, and there's also some radicals with 5th degree, 5th root, 4th root, and so forth. So first, before we get into how to simplify these, let's review how to rationalize the denominator with just square roots. So previously, we've learned that with radicals, when we simplify them, we can never leave a radical in the denominator. So in this case, even though we can follow the property that we just reviewed by separating this numerator and denominator, the problem is there's nothing else we could do. Neither of those numbers can be broken down any further, or neither of them are perfect squares or anything like that. But then we run into a problem because we're not allowed to leave a radical in the denominator of our fraction. So that's when we have to rationalize the denominator. Now, in order to get rid of the radical in the denominator, because a radical, if you multiply it by itself, square root of 2 times square root of 2 would be square root of 4, it becomes a perfect square, which then you can solve. So what we would do is multiply both the numerator and the denominator by whatever that radical is on the bottom. So now, on the top, we have square root of 10, and on the bottom, as we said, square root of 2 times square root of 2 is square root of 4, and that's solvable to just 2. So that would be our rationalized answer there. So let's try another example. So again, if we have a quotient inside of our radical, we can always use those properties to separate it. And sometimes that does help us. Sometimes these numbers that we end up with are perfect squares that we can solve, or they're numbers that can be simplified using our factors. But in this case, we're as far as we can go, right? So now we're going to multiply both the numerator and the denominator by that same radical that we have on the bottom. So then on the bottom, when we multiply radical 3 by itself, the radicals basically just cancel out, and we're just left with 3. On the top, however, 7 times 3 is 21, and they're still going to be inside that radical. And that would be our answer there. Now, in both of these cases, 10 and 21 there's no factor pairs. So if we did our tree, you break down 21, you're just going to get 3 and 7. There's no pair that can come out. Same thing with the 10. You break it down into 5 and 2. There's no pair to come out. So there's no more simplifying you can do with those. So let's see how this works with other types of roots. So for example, if I'm going to do a 5th root, well, first thing we're going to do is separate it, right? So we have the 5th root of 3 on the top, and then the 5th root of the 4 on the bottom. Now, what I want to do here, however, is that I need to get a group of 5 of the same number in order to take it out. Just like here, since they were square roots, I needed 2 of the same in order to pull it out. Now you could technically do 4 more 4's to get a total of 5, but you want to work with smaller numbers. It's going to make that a little bit easier. So first let's break down 4 as factors, right? So if I did my little factor tree for 4, it would just be 2 and 2. So now I'm going to write down on the top 5th root of 3. On the bottom, I'm going to have the 5th root of 2 times 2. Now the reason I'm doing that is because I need to have 5 of the same thing in order for me to get rid of that radical. So if I already have 2 2's, I would need 1, 2, 3 more 2's. And whatever we do to the bottom, we also have to do to the top. So I'm going to put 3 2's on the top as well. So my marker's kind of dying there. So now on the top, we have 3 times 2 times 2 times 2, which works out to be 24. And on the bottom, since I have 1, 2, 3, 4, 5 2's, I'm just going to take out that 2. Now, if you did multiply it all together, 2 times 2, so forth, you get 32. The 5th root of 32 is solvable to 2. And we know that this 24 can't be simplified because we already had it broken down into the factors here, and there were never a group of 5. So this is as far as we're going to go for that problem. So let's try number 4. So in number 4, again, I'm going to separate it. The top number, you're just going to write it exactly as it is. It's still in a 4th root. On the bottom, however, what are my factors of 8, right? 2 and 4, 2 and 2. So I can rewrite that as 3 2's being multiplied together. So now, how many more of those 2's do I need to get this group of 4 so that I could take that 2 out of my radical? Well, I already have 3, so that means I'm going to need 1 more 2. I'm going to multiply that on the top as well. So now in the numerator, I have 7 times 2, which is 4, 4th root of 14. And then on the bottom, since I have 4 2's, I can just take that 2 out. And that would be my answer after I've rationalized that denominator. Okay, number 5. So this one, 2 and 3 are already prime numbers, so there's no factors I need to break it down into or anything. So basically, I'm just going to go ahead and split it up. And now on the bottom, I'm going to need how many more 3's? If I need a total of 4, I already have 1. So 2, 3, and 4. Add those extras to the top as well. So now my numerator, I have 2 times 3 times 3 times 3, which I believe is 54. And on the bottom, since I have 4 3's, I'm just going to take out my 3. And that would be that one. And then finally, this number 6 here, the 1458, that would break down. This is just the one we were doing on the last set. So 2 and 729. I believe this breaks down into 9 and 81. 9 is 3 and 3. 81, 9 and 9. Each of those break into 3 and 3. And so now I need a group of 5 in order to take something out. So we've got 5 3's, and then this 2 and this 3 here are going to stay inside and multiply back to 6. And that's our answer for that one as well. Okay, so now let's do a couple problems where we do some addition and subtraction with radicals and see kind of how that works. So the key is, just like with a lot of things in algebra, we want to combine like terms when we're adding and subtracting. Well, what are like terms when it comes to radicals or rational exponents? So when it comes to exponents, we're already pretty familiar with adding and subtracting like terms. It means that they have the same variable, the same exponent, and that kind of thing. So here, 7 to the 1/3 and 7 to the 1/3, it's no different than having like x to the 1/3 or something like that. So we know those are like terms, and then we just add or subtract those coefficients. The same rules basically apply for radicals. So in this situation here, number 1, we have -8 times the 4th root of 13 plus 17 times the 4th root of 13. So in both of those, they have a common or like term. They're both 4th root of 13. So then we're just going to take the numbers in the front, the -8 and the +17, and combine those. So -8 and +17 are going to give us +9, and then we still put on that like term of the 4th root of 13, and that would be our answer there. Now for number 2, when we have rational exponents, like I was saying, these have the same base with the same exponent, so you're just really combining those coefficients. So 3 minus 16 is -13, and then they both have that same like term there of the 7 to the 1/3 power. And that's all we would have to do for this, combining those. Now, when we get down to numbers 3 and 4, it's a little bit different because this time, even though they're both cubes, the numbers inside the radical are different. So what we would have to do in that case is simplify either one or both of them to see if they end up with the same radical. Now 5 can't be simplified any further, so we don't have to worry about that one. But let's take a look at the 40. So maybe over on the side, if you don't know how to do it in your head, you can kind of do your little factorization for 40. So if I do 2 and 20, 2 and 10, 2 and 5, it's a cube, so I have 3 2's, so I know I can take out that 2, and then that would leave me with this 5 left inside. So now I can see that I'm actually adding 2 times the cubic root of 5 plus 11 times the cubic root of 5. Now I have 2 like radicals. They're both cubic root of 5. So I can now combine those coefficients, and I can get the 13 with the cubic root of 5. So same thing applies here with number 4. Obviously the 5th root of 3 cannot be simplified any further, so I don't have to worry about that side. But the 96, I'm going to have to see if that can simplify. Hopefully I'll be left with a 3 inside my radical. So if I'm going to do 96, you break it up however you want. I'm just going to go ahead and do 3 and 32. And from there I can do, let's say, 2 and 16, 4 and 4, 2 and 2, 2 and 2. And again, doesn't matter what way you went about doing that, you should end up with 5 2's and 1 3. Now because I have my 5 2's here, I know that I'm going to be able to take out a 2. And then I have this 1 3 left inside, which is great. I was kind of hoping for that, right? And then there's a 5th root there. Now you might be like, hey, wait a second, there's already a 2 here. So what happens is this 5th root of 96 simplified into this 2 times the 5th root of 3, but there's already a 2 on the outside. So that becomes 4 times the 5th root of 3. And now we can add that to the other 4 times the 5th root of 3. Combining those two coefficients would give me an 8. And then my like radical, which is 5th root of 3. Okay, so now we're going to simplify some radicals that have both numbers and variables inside. So if we want to look at a term like this, right? Usually I kind of look at the number because we already know how to sort of deal with that, and then I kind of focus on the variable after. So if I'm taking a look at this, just like we've learned the properties previously, you could actually kind of break apart these two portions of the problem. You don't necessarily have to write them down separately like that, but I kind of attack them that way mentally. So if I'm looking at the 125, that's pretty straightforward. We can just do our factor tree, right? So 25 and 5, 5 and 5. Okay, so we can see that the 125 has a group of 3 5s, which means that 5 is just going to come out. Now, if I want to look at my y to the 6th power, really, what does that even mean? Well, it means that I have 6 y's. 1, 2, 3, 4, 5, and 6, right? So if I need a group of 3 to take one out, well, here's one group of 3. Here's another group of 3. So I'd have a y come out for each one, so that would give me 5y squared as my answer. Now, a quicker way to do that, if you have 6 y's and you know you need a group of 3, you can simply just divide 6 by 3, and that will give you the 2 that you're going to have here, 2 y's. So let's take a look at the next one. So again, the 16, you want to do it over on the side or mentally, right? So I have 4 and 4, 2 and 2, 2 and 2. So it works out that a group of 4 2's. Now I'm going to look for my x to the 20th. So if I have 20 x's being multiplied together, how many groups of 4 can I get? Well, 20 divided by 4 would give me 5 groups of 4 x's. So my answer would be 2x to the 5th power. Then finally on number 3, okay, this time if I go to break up my 10, it only goes down into 2 and 5. Clearly there's not a group of 5 factors that are the same. So we know that that's going to stay in there. Well, let's look at the x to the 15 now. So if I have x to the 15, how many groups of 5 am I going to get out of there? Well, 15 divided by 5 is 3, so I'm going to end up with x cubed. And then the y, I have 25 y's. How many groups of 5 y's can I get? Well, 25 divided by 5 is 5. So I'll have y to the 5th. Now, the x cubed and the y to the 5th are just normal variables now. They're not inside the radical any longer because we divided the 25 by 5 and got 5. The 15 was divisible by 5 and got 3. But the 10, we were not able to take anything out of there. So that part stays inside the radical. Okay, so we have a couple more radical problems to simplify. This first one is a quotient inside the radical. So I'm going to start out by breaking it up into that separate numerator and denominator, both of course being 6th roots. So now that first one, again, we have that even number. So if we have 6 x's inside, we would have one group of 6. So that would just equal x, or x to the first power. Then on the bottom, 18 is divisible by 6, so that would give me 3 groups of y, or 3 groups of 6 y's, and then that would be my answer. I no longer have a radical in the denominator, so I don't have to worry about rationalizing it or anything along those lines. So number 5 is a little bit different, because this time we have 3 different amounts, or 3 different numbers in here. So we have the 7 on the x, the 12 on the y, the 11 on the z, but not all of them are divisible by 3. So that's going to create like a new challenge. So this first one, we have x to the 7th. Now what happens there is that 7, if I have 7 x's, okay, I need groups of 3. So here's one group of 3, here's another group of 3, but I still have this one left. So what happens in this situation, it's kind of like dividing and you get a remainder. So if I divide 7 by 3, I get 2. So I have x squared on the outside, but this little remaining x is still stuck on the inside. So now when we look at the y, 12 divided by 3 works out evenly to 4. So y to the 4th would be on the outside. There's no remainder for the inside. And then when we look at z to the 11th, the 11 is divisible by 3. We get 3 groups of 3. So we'll have z to the 3, and that would be 9 total. So there would be 2 z's left over. So if you kind of need a little visual for that, if I had 11 z's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, you can see 1, 2, 3 groups of 3. That's where my z cubed comes from on the outside. And these 2 extra ones is where that comes from on the inside. All right, so let's take a look at number 6. This time we're doing a 4th. Now again, I start out with my regular number here, which is 12. But as you probably already figured out, this does not have any groups of 4, so we're going to leave the whole 12 on the inside of that 4th root. There's nothing that can come out. So now we have the d to the 4th. 4 divided by 4 is just the 1, so we have just that 1d coming out. There's no remainder, so nothing left to keep inside. Then we want to look at our e to the 9th. 9 divided by 4 is 2, and there's a remainder of 1, so that'll be 1e left on the inside. And then we have our f to the 14th. 14 divided by 4 is 3. 3 times 4 is 12. There's a remainder of 2 f's left on the inside, so this would be our answer for that one. So now we have a couple more with the quotients, and so far we haven't done any quotient ones that don't work out nicely like the way number 4 did. So we'll start it out. So I have the 5th root of m to the 12th, and on the bottom I have the 5th root of n to the 19th. So we could just go ahead and separate it, right? So now what happens is you need this number to divide by the 5 evenly. But 19 is not going to divide by 5 evenly, right? Now it doesn't matter on the top if they divide evenly because you can still have a radical on the top. In order to make this radical go away in the denominator, we need it to work out to perfect groups of 5 so that there's no more radical necessary, right? So like remember this problem, we had 18 divided by 6 was 3, worked out evenly, so there was nothing left. So what else would I need? I would need this to be a 20, right? So I need one more n on the bottom, and then whatever you do on the bottom, you also have to do on the top. So now on the top, I have the 5th root of m to the 12th times n, and on the bottom, I now have the 5th root of n to the 20th. And of course, that should work out evenly and get rid of your radicals. So 20 divided by 5 is 4. So I have 4 groups of 5n's. And on the top, you might be able to simplify a little bit of this. So the 12 divided by 5 is 2, leaving you with 2 other m's inside. And of course, we also have that m inside as well. So this would be our answer for that one. All right, so let's take a look at that same thing with number 6, right? So in the bottom here, I have a to the 13th on top. I'm not going to worry about that just yet. On the bottom, I have b to the 10th, but I need a multiple of 6 there, and you can't decrease it. So, 6, 12, 18. So we need this to be an 18. So how many more b's do I need to make it 18? I already have 10, so I need 8 more. Oh no, wait, 2 more, sorry about that. And whatever we do on the bottom, we also need to do on the top. So now on the top, I have the 6th root of a to the 13th b squared. And on the bottom, the 6th root of b to the 12th. So now we're going to simplify them. b to the 12th on the bottom, 12 divided by 6 is 2, works out evenly, which gets rid of the radical. On the top, 13 divided by 6 is 2. But then we still have this extra a left inside and the b squared left inside as well. And then finally, our third problem. So here we've got 4th roots. So I'm just going to leave the top for now. And on the bottom, we already have z to the 6th, but I need a multiple of 4, so we need 2 more z's in there to make it an 8. And whatever I do on the bottom, I have to do on the top. So now on the top, I have x to the 8th, y to the 11th, and z squared. And on the bottom, I now have z to the 8th. So now on the bottom, since I have a group of 8 z's here, I need 2 groups of 4. 8 divided by 4 is 2, so I no longer need that radical there. And on the top, 8 divided by 4 would be 2. Works out evenly, so I don't need the radical for that one. 11 divided by 4 would be 2, with a remainder of 3. And then 2 is not divisible by 4, so that z squared is going to stay inside there. And that would be my answer for that one. And thanks for tuning in for me today for our lesson.